title of this talk is on disaggregation of packet optical networks. So to give you a bit of context, let me just start by showing what is the current evolution of optical networks. So basically, we have devices that moved from traditional hardware, quite large one, to much smaller physical devices. These pluggable transceivers, they are very small devices, and this change in the form factor, moving from large piece of hardware to small devices, is enabling the adoption of hardware chassis that need not to be specifically designed for optical networks, but we can also use switches and routers that have been designed for data centers, for example, or for traditional IP routers. So the market is much larger, and there are much more opportunities to do an effective integration of IP networks and optical networks. So the key enabler for this integration is basically the reduction from large devices to small devices, thanks to this technological evolution. And this is particularly effective, not really in ultra-long haul systems, but in scenarios like metro networks, where the performance of these devices that are small, so say, is more difficult to make the same performance of a larger device. But in metro networks, where the distances are in the order of few hundreds of kilometers, these devices work very well. So thanks to this integration, we have seen that to this miniaturization, we have seen, maybe there is some timer, hope. Oh, okay, hope we will keep it. So we can see that in the past years, there was a development of 10G systems and then 100G systems, and now the hyperscalers are moving to 400, and now we already surpassed these, and we are in the AI era, where 800, 1.6, 3.2 tera are provided with these small pluggable systems, which means that we can really are really able to transmit a huge amount of data with very small hardware and take advantage of this impressive market that is driving the evolution of this sector. And so also the telco sector, the telecom sector, can take advantage of this huge and impressive growth and technological improvement. And here, just to give you last slide, to give you a bit of context, is how the evolution is moving in the last years, where you can see an incredible amount of higher speed transceivers that at least are at 800G, but soon it will be they will be available at 1.6 and even 3.2 tera. So these evolutions come together with also the evolution of switches and routers. So because in order to support these high-speed transceivers at 800G and 1.6 and 3.2 tera, also the ASIC, the packet switching, the forwarding needs to be to keep up this space. But we can see that in terms of switches, the evolution is following properly. So basically, we are facing in the datacom market, in the data center market, a huge evolution that is happening in the transceivers as well as in the ASIC. So basically, this evolution gives us the possibility to move from a traditional scenario to an evolved scenario. So let's have a look at this scenario. In a traditional case, we have routers, traditional routers that, in order to cover long distances towards the cloud, for example, In the past, they always needed dedicated optical devices like transponders that were able to provide very good transmission performance, which instead in the router, you remember the large card, was difficult to also host a large card in a cost-effective way. So that we had a lot of these dedicated pieces of hardware, very effective in transmitting through an optical network the signals towards maybe additional routers up to the cloud. On the other side, towards the access side, we typically had aggregation routers that enable the connectivity, cell-side gateways to antennas for 4G, 5G connectivity. So this is traditional scenarios that use transponders. Now, what happens thanks to the evolution enabled by these small transceivers that can fit a next generation of routers that is mainly designed or takes advantage of data center operations. The benefit is that we can plug these transceivers within a router, an aggregation router that could even be a white box, a disaggregated box where we have an underlying hardware that is standard and that can be controlled through a standard interface. So as you can see, we are removing standalone transponders and have the transmission capabilities embedded into a router. Of course, there is still a slight difference, so we cannot maybe traverse thousands of kilometers as these transponders were able to do efficiently, but still in the order of few hundred of kilometers, this is very effective and also cost effective. So this is one step of the evolution. Actually, it's interesting also to see that this could happen on towards the access side, because now there are available point to multi-point pluggable interfaces, and as you can see, they could avoid also the presence of aggregation routers. So now imagine to be an operator. In the traditional scenario, you need to manage aggregation router, transponders, everyone with its own operating system, with its own management system that needs to be maintained, upgraded, it may fail. And now you are only managing a single device with a pluggable solution. So this is much more effective, particularly in this period where we are also introducing edge computing scenarios. So we do not always go to the cloud. We also provide some services at the edge, particularly for example, low latency application enabled by 5G, by 6G, and so on. So this network is much more compact, much more efficient and easy to be managed, and also less expensive. However, there are some challenges that need to be faced. One of them is the control of this unified, let's say, device. Traditionally, we had separation of a router and separated we have the transponder with the optical connectivity. So basically, we had in the traditional approach an optical controller that was in charge of controlling the transmission system in the transponder, all the switching, optical switching with the ROADMs up to the other side of the network where there was another transponder. So this optical controller was in charge of controlling this network, optical network alone, while the IP routers were controlled by a packet optical controller. So these nodes, this controller configured this router, the optical controller configured all the intermediate optical network. But of course, connectivity needs to be provided end-to-end, so from the router crossing the optical domain and reaching the router. So in the traditional approach, we have a hierarchical controller that coordinate the packet controller and the optical controller. So basically, what typically happens is that the hierarchical controller decides, okay, we need a connectivity from here to here, passing through an optical network. So let's configure the optical path from this transponder to this transponder. Once this connection is up, the IP connectivity sees a link that is up and gets active as well. So there is this coordination made by the hierarchical controller, but this coordination is quite simple. First, set up the optical connection, and then the IP connectivity will go up immediately as soon as the physical connection is up. But now, these two elements, the router and the transponders, are becoming a single element. So who is going to configure this unified element? The packet controller, the optical controller, both of them. How to manage this new type of device where there is no clear separation here. So there has been, in the last few years, a lot of discussion on how to address this solution, how to move forward from a traditional approach. Basically, there are two main approaches that can be considered. The first one is called single IP over WDM. Single, what does it mean, single? Single means that this new packet optical node, the IP over WDM node, is controlled only by the IP controller, the packet controller. So only one controller is able to configure, has access to configure this node. However, we don't have to forget that we still need to have the physical connectivity up. So, the transceiver here is the one that needs as well to be configured according to the wavelength, for example, the specific transmission parameters like modulation, the type of modulation, the type of forward error correction. So there are several parameters that need to be configured in this device, and they depend on, for example, the impairments that are experienced here. So if it is a very long connection, we need a more robust modulation format here, for example. Or if it is a short one, we can take a higher order modulation format. But how the router knows what is the distance here? Because this is known only by the optical controller. So in this case, you can see here an example of the evolution that is needed in the coordination between the two controllers through the hierarchical controller on how to manage this scenario. So let's assume first step, a connection request from here to there. And then this hierarchical controller first go to the optical controller and tries to understand what is the path here and how much impairments we need to cover, the distance, all the parameters. At this point, the optical controller returns back to the hierarchical controller all the details about the optical path that could be established here. With these optical parameters in mind, the hierarchical controller passed this information to the packet controller. The packet controller may not be able to even understand exactly what is this optical parameter configuration, but it pushes down this configuration to the transceiver here. And so at this point, the configuration should go up. So you see there is, compared to the traditional approach, we have an additional exchange of data. And in particular, this hierarchical node needs to, say, pass some information from one side to another. So it's is a bit more involved in the process. So we have to face maybe more scalability issues, some maybe delay, additional one. And this is one option that is called single. The single approach has the benefit, however, that only one controller is able to configure the node, only one. because the alternative option that is called the dual enables both controllers to interact with the same node. In the packet controller case, the configuration will be enabled only to play with the IP parameters, while the optical controller can play only with the transceiver parameter. So in this case, when we see the same scenario of a connection request, this connectivity that goes to the hierarchical controller and is passed to the optical controller, it can be immediately configured end-to-end, including the transponders in the transceivers here. And then, when this is acknowledged, the hierarchical controller pushes down the request for the packet connectivity, and so the IP connectivity is configured, and at that point the link is physically up, so the network is up. So this configuration is simpler. However, it requires that this node has dual connectivity to two different controllers. In principle, this can be done. There is also a specific standard that is described in this request for comment, A341, that specifies that it's just a matter of authorization. But practically, there are constraints that refer to, for example, what happens when the operator needs to update the operating system of the node, or to change the version, or maybe to change the software of the controller. So there are cases that kind of scare a little bit the operators to implement this dual scenario. So although it's simpler and faster, we can have to face some of these issues. So the debate is still open. Actually, it happens that some of the operators and some of the vendors prefer to have the dual option. For example, the dual option is liked by the vendors that provide, so that they are able, the vendors of the optical system, that they are able to provide, to have full control of their optical system. While, for example, the single solution is preferred by the IP routers that can guarantee, by the vendors of IP routers, because they can guarantee full control and unique control of the packet optical node. So there is kind of still open debate, but these are the two main solutions. Actually, we have implemented both of them. There is some slight delay in the single one because of this back and forth of the operations, but overall they work both fine. It's just a matter of preference and also management aspects to be investigated. So this is an example of the challenge that happened when we have to face to these new, on the control plane, of these new IP over WDM boxes that integrate both the switching part as well as the transceiver part. However, there are, besides those challenges, there are other potential benefits that can be exploited. One of these benefits that we are exploring is the in-band operations. So you see that these transceivers are the bandwidth, the capacity of this connectivity is getting larger and larger. A single transceiver can manage 800 gigabit per second, 1.6 terabit per second, in near future 3.2. So it's really an impressive amount of data. And also the ASIC here is able to cope with this huge amount of throughput. Consider that there may be 32 or even more 64 ports. And so imagine all these ports to go at that speed. So the ASIC in the middle needs to be able to process a huge amount of data. And there are versions of these ASICs that also enable some kind of programmability. A little one, but this programmability enables to maybe move some of the operations that are traditionally done in a control plane to be moved to the data plane, taking advantage of this huge amount of data. For example, in the past, when we have a connection at very low speed, consuming part of this bandwidth for some control plane in-band operation was maybe not ideal. But now with 800, 1.6 tera, even if we consume 1 megabit of traffic or 1 gigabit of traffic is really nothing compared to the huge amount of capacity that this network is providing. So there is a huge trend in the research community to exploit more and more in-band operations. In-band operations need to be efficiently supported. So we also, beside taking advantage of this higher capacity, we also need to be able to consume this information that are exchanged not in the control plane, but through the data plane. An example is reported in this slide. So in this slide, for example, we have these bidirectional connections between two IP over WDM nodes. This transmission transceiver, the transmitter side of this transceiver is sending traffic to this node. This node in the transceiver receives this data. It detects properly, and it also provides some pre-forward error correction bit error rate performance. You can see in this scenario that this node on the right-hand side is not really aware of the performance experienced by the other node of the signal that is sending, because only this Rx on the other side sees the actual prefect bearer performance. So traditionally, to become aware of this of the performance of X own transmitted signals through the control plane, there was a telemetry system and a centralized telemetry system that supervised all these operations. But now we can take advantage of this high speed and the high programmability of this node. And for example, we can, in this node on the left-hand side, read the experienced prefect bit error rate and send back through the data plane specific packets that include this prefect bit error rate. So this node on the right-hand side will be able to receive the measurements performed by the other node on the quality of transmission on this link. And at certain point, suppose that these measurements goes very bad because there is some limitation, some impairment, an amplifier doesn't work here in the middle, there is some issue. Maybe this node, by reading this telemetry data in the network, it can directly move traffic to a pre-configured alternative path, avoiding this maybe damaged link. So normally these operations that always were required intervention of the control plane now can be efficiently made, particularly in case of soft failure where it's not just a fiber cut that this node can detect by looking at the received side. But for degradations of the signal, these had to go through the control plane. In this case, this can be done efficiently in the data plane and very fast. So this is an example of operations that can be all performed in band. This is a slightly more complex scenario, but the idea is the same. So we were looking just consider N1, N2. We were just looking at one link. And we said, okay, if this node sends back the experienced quality of transmission by the signal that is received here, this node is able to take another direction. But in another direction, most probably there will be another node. So we need to implement this solution, taking into account that there are also other nodes. And so what happens? We have this working path, then suddenly something happens, and this node is aware that there are two alternative routes, but is not aware of the performance experienced by this link, by this link, this link, this link. So it doesn't have enough visibility, but it's not a problem. We can apply the same exchange of telemetry data from node 1 to node 2 that inform node 2 about the performance of the link from 2 to 1. We can apply the same about the link from 3 to 1, from 4 to 1. So at the end, node 2 can collect telemetry data that refer to the link from 2 to 3, from 3 to 1, from 2 to 1, from 2 to 4, and from 4 to 1. So in a restricted area, of course, otherwise maybe it would be too much, it doesn't scale, but in a restricted area that covers a working path and 1 or 2 backup paths, this node can become aware of all the real-time performance experienced in all the network, and not only the quality of transmission. It could be also the actual occupied bandwidth, because with traffic engineering, we don't have always the full visibility on the actual bandwidth that is occupied by the real traffic. So here we can enhance this telemetry with a lot of pieces of information. So there is this evolution that is quite interesting. Sorry. Towards this in-band control plane. Now, before closing, I would like also to give you another of small pieces of research directions. One is the use of smart NICs or network interface card that could be as well equipped with the pluggable transceivers. And so this represents the convergence of packet, optical, and also computing resources. This is another interesting research topic, particularly interesting for 5G scenarios, where we have mobile sites that are decentralized, so distributed. We have some functionalities at the mobile site, some other at the local central office, some other at the regional central office, sometimes at the national central office. And in some cases, these are virtualized resources that run in a server. And so installing pluggable coherent transceiver in the servers is an interesting option. And so this is another research activity. So to see the pluggables inserted into computing resources. So basically, this concludes my presentation. If you have questions or if something was not clear, happy to answer. If there is time, I don't know, maybe it was too long. Yeah, sure. Yeah, Akiwa.
The in-band optical monitoring. So since it's now, the monitoring is now happening in the data plane, do you have like dedicated channels for this? Because you obviously you're not doing it in the same channels as for the data itself.
No, actually, the idea is to exactly have it in the same channel. So you have this connection at a specific wavelength, and this is this connection in an IP node is terminated electronically. So it goes into an ASIC. And so you can, in this ASIC, consider that this has the capability to manage all these packets from 32 port at this high speed. So it's a very powerful ASIC. And so this ASIC can recognize this is a telemetry packet. It's not a data packet that is, I don't know, some application, some web applications, traffic from customers. It has a specific header. So this node can detect that this is a telemetry packet and process it, like, for example, enforcing a change in the configuration. Good. Any other question? Yeah, Federica. Oh, hi, Federica. Yeah.
Hi, Filippo. Hi, nice to meet you
Hi.
again.
Yes. different context. Yeah.
Exactly. Can I ask you if you can spend a little bit more words about the last topic that you showed us, the
Yes.
DPU? I mean, I'm not
Yes.
very
Yes.
sure. Yeah,
Yeah. I
exactly.
just briefly mentioned because of lack of time, but this is a topic, a research topic that I like very much. Basically, because what happens in intermediate routers, traffic is there is so much traffic that you cannot really do a lot of operation. You cannot even store anything for processing because it's too much the traffic that you can manage. So it's just a transit element. You cannot really do a lot. Instead, in a network interface card, traffic is typically terminated in the edge here. And so the amount of traffic that this node manages is the one that is terminated in the edge. So it cannot be too much, even if it is 100 gigabit ports, for example. This node is able to manage this amount of traffic. Is not encrypted typically because encryption happens exactly in the DPU or in the smart NIC or in the NIC, while here in a transit node, everything is encrypted. So here there are a lot of opportunities to perform deep packet inspection, security, to do a lot of operation. So traditionally, these are separate elements. So we have a server that does the encryption with a regular NIC that sends the traffic to a nearby router that is then used to make the connectivity to long distances. But with this pluggable, we can now imagine to plug these pluggable transceivers within the network interface card of the edge node. And for example, the edge node can directly send the traffic to the cloud without being aggregated in a router. It just needs to be configured with a specific wavelength. And it can also then take advantage of all the capability of a network interface card that is smart, like the DPU, which is a lot of security capabilities, deep packet inspection, a lot of interesting operations that can be done using the hardware in the NIC. I don't know if.
Thank you.
Yeah. Yeah, Joseph.
Thank you, Filippo. I have one question related with the telemetry of the transceivers, in this case for the coherent pluggables. Something that I am quite interested about this is related with the prefect and the noise variance that you can have, because right now a lot of these pluggables are working with shaping, which produce a really weird type of noise. So usually this the prefect that you are defining is something fixed or is changed depending on the requirement of the network?
So in this case, the prefect bit error rate is the actual measurement that is made at the receiver side. So it gets all the signal that is generated from the node on the right, and here the receivers needs to reconstruct the electrical signals. So it gets all the sequence of bits, and it is able to understand what is the actual experience bit error rate. In this transceiver, there is the forward error correction. So after this receiver, what enters into the router, into the switch, is a clean signal that has no errors. If it has error, the signal goes down. So the connection is turned down. So what happens here in the yellow is without errors. However, before the forward error correction, so pre-FEC, we actually have bit error rate that, however, is recovered by the FEC system. This pre-FEC bit error rate is a very nice indicator of the quality of transmission in this signal. So being able to read this pre-FEC bear enabled us to understand how far we are from the limit, how can be we make the transmission more efficient? Because if we look just at what enter into the ASIC, it will be error-free. So here we can see, for example, among the possible parameters, prefect bit error rate or the received power of the signal. So these are the two main parameters that are that nowadays can be read by the operating system of a switch. To get more advanced monitoring features, we need to have the DSP here being able to detect, understand, and also make available additional parameters. But nowadays, prefect bit error rate and received power are always available.
Okay, that is interesting. But my point is, like, in this case, do you want to the telemetry in this case is working like with a certain fixed prefect that it will ensure a clean signal on your programmable in your switch? That I understand.
You mean a threshold? A
yeah, the
threshold,
exactly.
Yeah, exactly.
But for example, in this case, please. In this case, if you are looking right now, you are trying to look something with more degrees of freedom, in the sense that it can be adapting to the different type of channel in the different type of requirement of the user that you can have. In this case, to expand, for example, the bandwidth that is required, it will change the channel coding that we are using. So we should have different type of FEC or prefect, and so that is my question. Are you trying to look in this moment like something more like that gave you more degree of freedom?
So if I understand correctly, yes, for a specific transmission configuration, we will have a specific threshold. If we change the conditions, the threshold may change. It depends. But in general, with this prefect bit error rate, you can define threshold and then take actions. If the threshold is exceeded, consider that you also cannot say exceed. You cannot just move the traffic if a single sample exceeds the prefect threshold. So you need a kind of hysteresis, you need a kind of intelligence here in order to manage this data properly and just avoid to move traffic continuously from one link to another. So this is just a simple example to show the idea. In terms of implementation, we need to configure it properly in order to avoid these continuous changes, and in order to have parameters that adapt according to the actual transmission performance and configuration. Yes, I don't know if this was the case.
Thank you very much.
Okay.
Yeah, yes. Thank you very much.